This is section 10.6, and we're just going to look at how to apply growth and decay functions. That's exponential growth and decay, and we do use that as an application often in real-world applications and business applications. And so when you see this general formula, it might be a little different in places, but it's y equals y sub 0 e to the kt, and y sub 0 is the amount at present, so that's at time t equals 0, and the quantity is said to grow or decay exponentially. So that means if we talk about exponential growth, that's the kind of formula we might have. Here's an example. Yeast in a sugar solution is growing at a rate such that 1 gram becomes 1.5 grams after 20 hours. Find the growth function assuming exponential growth. So here's our general equation, and we're saying that 1 gram turns into 1.5, so we can make y sub 0 be 1 and 1.5 be here. E to the t is time, 20, k, and we don't know what k is. We're looking for k. So we take the ln of both sides. Remember, we've got to get that exponent down here. So ln of 1.5 equals ln of e to the 20k. ln and e are canceled out, so we have 20k equals that. We divide by 20, and k equals 0.202. So that would be your rate. Actually, it would probably be a percent. Or we might have carbon 14 problem, kind of like a half-life. The amount of carbon 14 present after t years is given by this exponential equation. So this is how much is left is equal to a sub 0, what you start with, e to the kt. And in this particular problem, k is equaling this, and they're not changing that to a decimal approximation. They're going to use that exact. So since it's half-life, we can have half of a sub 0 equals a sub 0 e to that k times t. Well, as you could see, the a sub 0's cancel out, so now we have 1/2 equals e to that exponent. We'll take the ln of both sides. ln of 1/2 equals ln of e to this. That ln and e are gone, so we have ln of 2 divided by 5600, all of that times t, and this is negative, equals ln of 1/2. We're going to divide both sides by this, and so we get, this is our approximate, and if we do that all on the calculator, we'll get 5600, and I thought that I had that on the calculator, but I do not. You could use ln 0.5, that all in parentheses, divided by, and then be sure that all of this is in a separate parenthesis. That will make sure that you get the right thing. All right, we only have 3 problems in this section, so let's look at those. Find the present value of the following future amount. So we're given $200,000 what we're going to end up with, and we're trying to solve for P. So plug in everything that you have. This is 0.09. We're quarterly, so we're over 4 raised to the 4 times 15. So we've got 200,000 equals P times this to the 60th. Go ahead and raise that to the 60th and then divide that over here, and we have 52,629.71. That's the amount that you have to start with in order to end up with 200,000 in 15 years at that percentage rate. This is the same one, except this is continuous. And we have 50,000 equals PE to this amount. So we're doing the same process. These two were really easy, and I threw those in there for you. Then we do have one half-life problem. Half-life of a radioactive element which decays according to the function. And here's our function. And so we're supposed to find the half-life. So again, we say 1/2 equals 1 e to the negative 0.0357t, ln of both sides. So now we have ln of 1/2 equals negative 0.0357t. Divide both sides by this. So here's our approximate amount. I did that one on the calculator, and you got 19.4 and a long decimal. It says round to the 10th, so we have 19.4. So that's just a few problems where you're getting used to using exponential functions and applications.